Hello, my name is Martin Woolley. I'm a member of the BlackBerry Developer Relations team. In this video presentation, I'm going to be talking about an application I've been developing with my colleague John Murray, who's also a member of the Developer Relations team, and we're both based in the UK. The application is a vacation request or annual leave booking application. Now, which of those names makes most sense to you probably depends on whether you're British like me or not. But the essence of the application, whatever we decide to call it, is that it allows employees to submit requests to take time off work such that their manager receives those requests and can review them on their BlackBerry smartphone, and depending on how they're feeling that day, either approve them, or if they're feeling particularly mean or power mad, reject them. Now, there's a lot more to a simple sounding application like this than perhaps meets the eye. And whilst we're actually still working on the application, I wanted to take the opportunity to talk about certain aspects of the application now. And when we've finished, by the way, we'll release the code. Now, like all good development projects, we needed some requirements. So I've sketched out the key ones here. Let's review them. First off, employees should be able to submit vacation requests for approval. They should be able to modify such requests. So for example, if you change your mind about wanting Monday off and instead you want to take Tuesday, you should be able to modify that request. You should also be able to cancel any bookings that you've made or requests that you've previously issued. The application should present to the user their annual entitlement, the number of days they're allowed to take off each year, and tell them how many days they've currently used. Managers should receive and be able to process approval requests. It should be possible to use the application offline when there's no network coverage of any sort, with no compromise in the functionality available, and really without the user being aware that that's the case. An application like this needs to work with a back-end system that's been deployed by the enterprise. Now, there could be any such enterprise back-end system. We don't know that in advance. And our brief was to try and make things as easy as possible for developers needing to integrate this application with the particular back-end systems that their company uses. Now, I've highlighted the last two of these requirements because John and I saw them as being potentially challenging depending on which SDK we chose to implement our application with. So let's talk about that issue next. Now on BlackBerry 10, you've got lots of choice. You can develop applications using our native SDK with the Cascades user interface framework. You can use BlackBerry WebWorks using HTML5 with native code extensions. You could create a pure HTML5 application with no native code at all. Or you could develop an Adobe Air application. You could even develop an Android application which, provided you don't use APIs that the BlackBerry Android player does not support, will run on BlackBerry 10 just as it does on an Android device. Now, John and I considered native, BlackBerry WebWorks and pure HTML as our options, and we felt that the key points for each were as follows. Using the native SDK, we'd get full access to device, APIs, and platform services. So in other words, if it could be done, then we'd be able to do it through the native SDK. And we'd get the best performance possible as well. In fact, you can produce blisteringly fast code using the native SDK. But the result would be a platform-specific application that would only work on a BlackBerry 10 device. Where BlackBerry WebWorks was concerned, we'd be producing a hybrid application which used HTML5 for the user interface and native code via extensions to exploit capabilities of the device via its APIs and exposed services. This would give us the potential for a good, rich, functionally capable application and the potential to reuse parts of our application, the UI written in HTML5, across other platforms. A pure HTML5 application, on the other hand, would not have access to device APIs except where these are exposed via standards. The result, however, would be a cross-platform application, which, depending on detailed capabilities of browsers on other platforms, should work anywhere. We decided to develop a native application first, and then later develop the same application or something very similar using pure HTML5 so we could compare the results and the experience. What I'm going to do here in this presentation is talk about the architecture of the native application as it currently stands. I'll start with a high-level overview. Then I'll take a closer look at each of the key architectural components one at a time. Our application has two key parts, and these are shown in green. An application which provides the GUI for the users to interact with, and a headless service which runs in the background. Using a headless service was key to creating an application that could work seamlessly when offline, i.e. when there was no network coverage, all as if by magic, without the user needing to do anything special at all, and hopefully being completely unaware that in fact there was no network available. So we'll examine this idea in more detail soon. Now on the right hand side, there's an orange box labelled adapter. This component is concerned with back-end system integration. At the bottom of the diagram, you can see two queues indicated, one labelled in and one labelled out. The queues and an internal API we called the Operations API form the mechanism by which the GUI and headless applications communicate with each other. And on the left you can also see the BlackBerry 10 hub mentioned. We make good use of hub integration and notifications in our application. We'll take a closer look at each of these components shortly. Before we do though, it might help to see a preview of the application as it stands today. Now, like I said, it's not finished yet, but what we've developed so far should help to make clear the way the architecture works. There's a tab or a page in which we list annual leave requests that the user has issued and their current state. Now I'll talk about state indications and the kind of workflow in our next slide. There is of course a page where we can enter details of a vacation request and submit it. And there's an inbox which predominantly is for managers to receive approval requests into. So when an employee submits a request for a vacation, their manager should receive into their inbox an approval task record. The manager will review it and either approve or reject the request. And the final screenshot I've included here shows the screen that the manager would use to do just that. Let's talk about states. I hinted at the fact that there are different states that requests and other record types can be in the previous slides. States are indicated in our user interface by icons of different types and different colours. As a first example, when a user submits a vacation request, initially the request is deemed to be pending. And when in a pending state, a request is simply sitting in the outbound queue on the device that hasn't yet left the BlackBerry device and arrived at the enterprise backend system for processing. That's the next state. Once that has occurred, the request is said to be in the submitted state. Now, at some point later, either very, very quickly after submission has occurred or much later, days, weeks, or more, our application will receive an indication from the backend system that the request was either approved by the manager or rejected. In exactly the same kind of way, if the user decides to cancel a vacation request that they previously issued, their request will go through 3 of the following 4 states. Initially, it will be called pending, and just sit in the outbound queue on the device. Once transmitted by the headless service via the adapter to the backend system, and we'll look at that in more detail shortly, the state of the request becomes submitted. Once processed, if successful, the request becomes cancelled. That's a final outcome. Or if it failed or was rejected by a manager, for example, it becomes rejected. In making changes to existing requests, we progress through an update workflow. Once again, the initial state is pending with the request sitting in the outbound queue on the device. Once transmitted to the enterprise backend system, it becomes submitted. And finally, it's either deemed updated once successfully processed or rejected if it failed or was not authorized. As you will have spotted, we're using colors also to correspond with those four possible states. So yellow for pending, still on the device, green, transmitted to the backend system, white, completed with a positive outcome, red, completed with a negative outcome, rejected or failed or something like that. So let's now walk through each of the key areas of our architecture, starting with the adapter framework. Now, the purpose of the adapter framework is to allow developers to plug in adapter components that they have developed. An adapter component is responsible for providing an abstract interface that the remainder of the application can exploit without having to worry about what actually happens when using it. And on the other hand, the abstractor is responsible for implementing specific methods for interacting with the particular backend system in use for vacation requests and workflow. This could, for example, mean using SOAP with XML for requests to the backend system, and perhaps using BlackBerry Push for receiving asynchronous updates and approval tasks from the backend system in the other direction. But in theory, anything's possible. Note that in our architecture, only the headless service interacts with the adapter interface. Now, John and I have implemented a number of adapters so far. A dummy adapter that simulates responses and state transitions, which we found useful during development. We also have an email-based adapter that uses JSON encoded data transported in the body of emails as the means of integrating with the backend system, which has an email interface. And we've also got what we call an email peer-to-peer adapter. This is really just for demonstrations. It uses email as the transport mechanism, but sends emails from device to device for direct processing by the application on each device, with no backend system involved at all. So the concept of the application can be demonstrated easily wherever we are, without being concerned about the particular backend system a company might be using. As you can see, the adapter framework approach is quite flexible. Now, you remember that one of our key requirements was that our application work and be easy to use when there was no network coverage. To meet this requirement, the architecture decouples the GUI from the processing of requests, and it achieves this through using a series of queues as a persistent store for requests and a headless service for processing them. In fact, we call requests operations, and just like a communications protocol, an operation has two parts: a request message and a response message. So for example, when the user creates a vacation request using the user interface, this results in a booking operation request message being placed in the outbound queue. The GUI tells the headless service that this has occurred using a mechanism I'll come to later in the presentation. And when there's network coverage for which the headless service is monitoring, it collects requests from the outbound queue, processes them, and then places corresponding response messages in the inbound queue to notify the GUI that this has happened. So in terms of our requirements, the benefit here is that the GUI can initiate any kind of operation without needing to worry about whether it can actually be processed immediately or not. Operation messages just get placed into a queue, and that's the end of the matter as far as the GUI is concerned. And to insulate the details of the queues themselves from both the GUI and the headless service, we provided an internal API called the Operations API, through which all operations messages are sent and received to and from the underlying queues. It's a nice technique that works really well in practice. Now, we've chosen to expose the fact that a user's request travels through various states as a consequence of this architecture, but you don't have to do that if you don't want to. You could present our pending state as submitted, and as far as the user is concerned, that would be that. If you're curious, by the way, our queues are just tables in a SQLite database. So, in summary, we have here a bidirectional, message-oriented communication mechanism between GUI and headless service. The GUI or the service creates a request message, issues it via the operations API, and later receives a response message. And here we can see the flow between the GUI when it sends a request to the headless service via the outbound queue. The service responds via the inbound queue, of course. So there we have our request created by the GUI being sent via the operations API, which stores it in the outbound queue. It then notifies the headless service that this has occurred. That request is then collected by the headless service by calling one of the operations API's methods and processed. And having processed it, it responds by creating a response, passing it via the operations API into the inbound queue. The GUI gets notified and collects that response message by making a call to the operations API, and the operation is complete. Similarly, the flow can happen in reverse, with the headless service sending a request to the GUI via the inbound queue. So for example, if we receive an approval task from the backend system directed at a manager asking them to approve someone's vacation request, that would arrive in the headless service as a request and stored in the inbound queue for the GUI to process. And the GUI, once having processed it, will respond to simply acknowledge that fact via the outbound queue. So here is an animation of that flow. First of all, the background service formulates the request, representing the event that's happened in the backend system, and uses the operations API to queue it in the inbound queue. The GUI is notified and uses the operations API to collect the object from the inbound queue. It processes it and then responds with a response message, which goes via the operations API back into the outbound queue. The background headless service is notified and uses the ops or operations API to collect that response message, and the operation is complete once again. So the GUI doesn't care whether a request can be processed immediately or not. We have a kind of fire and forget design here. There's no need to worry about whether or not there's network coverage. The headless service takes care of that. The GUI doesn't need to know about that detail. The headless service therefore processes the outbound queue when there's at least one request in the queue and there's network coverage of some sort, and it monitors the status of the different network interfaces to maintain an awareness of the availability or otherwise of network. Now, I've already mentioned the operations API several times, so let's take a closer look at that. Once again, it's an internal API used by the GUI and the headless service for interacting with the message queues without needing to know anything about their underlying details. It comprises a series of request and response operation classes, each sharing the same superclass. It's implemented as a singleton called operations with some public methods. And all operations classes are serializable via marshal and unmarshal methods. To achieve serialization, we used Qt's QDataStream class, and that was extremely easy. I'll show you some code relating to that on the next slide. And the reason we do that is it allows us to store serialized data from each of our operations objects as a binary large object in our database queue tables without being concerned about the original object type and the different fields that they may or may not have. So this is what the code looks like from one of our operations objects for both marshalling and unmarshalling our object's data. So the purpose of the marshal method is to take the attributes, the fields of our object and transform them into a Q byte array, which we can then store directly in the database as a binary large object. So call the marshal method, and whatever our member variable values are, they get serialized to a Q byte array, which we can then store. The unmarshal method does the reverse, of course, and takes a Q byte array as an input parameter and uses QDataStream once again to reverse the procedure such that we can populate our member variables with data extracted and reformulated from the Q byte array. So I've mentioned a few times that there are occasions where the GUI will somehow tell the headless service that there are operations in the outbound queue waiting for it to process, or conversely, that the headless service will somehow tell the GUI that there are operations in the inbound queue for it. But how exactly does one tell the other something? Well, the answer is we use the invocation framework, which is a really great feature of BlackBerry 10. So the GUI tells the headless service it has some work to do using the invocation framework. On receiving the invocation, the headless service asks the operations API for the objects in the outbound queue. And the operations API delivers that list of one or more operations objects for the headless service to process. And the same can happen in reverse. The headless service can notify the GUI that there is some work for it to do, again using the invocation framework. So this time the headless service uses the invocation framework and sends an invoke request to the GUI. On receiving the invocation, the GUI asks the operations API for objects from the inbound queue. And the operations API reads the inbound queue table and returns the objects to the GUI for processing. Now, if you're not familiar with the invocation framework on BlackBerry 10, we have lots of examples elsewhere, in particular in our GitHub repository of sample applications, but here's some sample code. I create an invoke request object and populate two of its attributes. I specify a target. This is an identifier for an application that I wish to invoke. And I can also set an action, which is an indication of what I want that application to do when it receives the invocation request. So in this case, I'm targeting the GUI application, and the action will indicate that there is some data in the inbound queue for the GUI application to process. We have a class called invoke manager, and I use its invoke method to actually fire off and execute the invocation request. We use notifications and the hub to make life easy for the user. Now, hopefully you're familiar with the hub on BlackBerry 10 devices. It is the place where all notifications are typically collected and all messages of all types from all applications that produce or consume messages are collected together to make life really easy for the user. So users are totally used to working with the BlackBerry 10 hub. Great way to inform them of things that are happening without being obtrusive. Since they're used to the hub, your application populating the hub with notifications is a very natural thing for the user. It's easy for them to find. And they act upon notifications when it suits them. It's not mandatory that they act upon them immediately. Now, as a developer, you can embed an invoke request in the notification so that when the user selects the open action associated with the notification, your application can be launched. So on screen, we have a screenshot of a notification sitting in the hub. If we were to open it, this is the content that we'd see, and you can see there's an open icon at the bottom of the notification. Now, in our application, we've populated the notification with an invoke request that will cause the vacation request application to be launched when the user touches the open icon. Now, before we finish, I'd like to make some observations. I think it's fair to summarize our requirements in these 3 lines. We had some create, update, and delete transactions that we had to support. We needed to support offline working with no compromise in functionality, and we wanted to make the user's experience of that as seamless as we possibly could. We also had a technical requirement. We needed to make integration with back-end systems as easy as possible. The observation's straightforward. John and I both think these are very common requirements that you will encounter in all manner of enterprise application, and therefore we suspect that this type of an architecture might be quite reusable across a great many different scenarios. It's certainly flexible. It maps to many common use cases. You can invent types of operation relating to anything you might want to do via your user interface. It's extensible. Again, you can add different operation types, and through the adaptive framework, you can accommodate many different types of backend system. And we think it's a robust architecture. It has well-defined interfaces and good, clean separation of concerns. Well, that brings us to the end of my video presentation. I hope you found this useful and interesting. I'll leave you with a few other pointers to resources you might find useful. The place for BlackBerry developers is developer.blackberry.com. You'll find everything there you could conceivably want to find out about developing for BlackBerry 10. We have an awful lot of great sample applications with full source code. The primary place to go and look there is github.com/BlackBerry, and the repository that most of my work and John's work will be found in is the Cascades Community Samples repository. Finally, if you'd like to follow John or I on Twitter, our Twitter handles are there on screen. That's @MDWRIM for myself and @JCMRIM for John. Thank you for listening.